Hello everyone and welcome to this video about logistic regression. This video is part of the course the minor clinical research principles and practice, and we're going to be covering a logistic regression model, in this case for prognostic research. So last time we did some data editing and after that we did some univariate analysis. And before we're going to go into the logistic regression analysis, I'm going to show you a little bit of a link between regression modeling and thereby multivariate regression and the univariate analysis. So first, a little bit of basics about regression modeling. So here, for instance, we want to relate systolic blood pressure to the outcome. We can do this with a linear regression, for instance, where we use the systolic blood pressure in this case as the outcome. This is only for the example. Usually you would not do this way, but for this example we'll use systolic blood pressure as the outcome, and the independent variable will be our outcome variable. And we'll want to see the R squared. No, not to change, only estimates and the confidence interval. Yeah. And run this. So here we see our regression model. This is the correlation coefficient, here the R squared. So a correlation of 0.19 between the systolic blood pressure and the outcome. And here we see that the intercept. So for people who have the outcome value of 0, who were censored, the average blood pressure was 132.8, and for people, this beta coefficient for people who did have the outcome, so value 1, they had a beta coefficient of 8.2, meaning that their average blood pressure was 8.2 mils mercury higher at baseline. And this is statistically significant with very low p-value and confidence interval 5.2 to 11.2. Now I wanted to show you this because this is in essence the same as a t-test, and I'll show you. So we do the compare means, independent sample t-test. We only include the systolic blood pressure for now. Run this, and here we have the t-test, and you see again these values correspond, right? Also, these confidence intervals correspond. So basically, what a regression analysis, in this case a linear regression analysis, is a more general version of a t-test. A t-test you can only do with a yes-no variable, whereas a linear regression analysis you can do with any variable. So these two things are interrelated, and this is nice to know. What you know about univariate statistics can usually be done in a regression model as well. And this also is the case for a logistic regression model. So basically, a logistic regression model is the counterpart of your cross tables, where you have a yes-no variable as the outcome. So let's run a logistic regression model. We go to regression again, and now we go to binary logistic. In this case, the yes-no outcome is the doubling of serum creatinine or renal replacement therapy, yes or no, and we'll relate that to systolic blood pressure. And this makes more sense, right? This, in this case, the baseline is the covariate or the independent, and the outcome is the dependent variable. Let's check our options. We don't want any of these except for the 95% confidence interval for XP. In a minute I'll explain what that means. We click on paste, and we get the logistic regression. Alright. So here again, the case process summary. Basically check that all your patients are included. This is the coding for the dependent variable, and here we see that the people who have the outcome are coded as 1, which is what we want to have. And here, this is the at the bottom we find the interesting table, basically, which says variables in the equation. And here, this beta means is the log odds ratio. So the exponent of beta is the odds ratio, and this odds ratio of 1.02 means that for every millimeter mercury increase in systolic blood pressure at baseline, your odds of having the outcome go up with a factor of 1.2, so 2% basically. This may not seem like a lot, but you have to realize that blood pressure has a very wide range, ranging from systolic blood pressure from 120 to 180 or such. So increase in of 2% for each mil of mercury is actually quite a lot, and it's very statistically significant. So this flips our linear regression around a bit, and in the logistic regression, basically our outcome that we're interested in is actually the outcome. Now the nice thing about logistic regression is that you can do this not just for the one variable, but you can do this for a whole bunch of variables. So we can take this, simply copy, and paste, and instead of only using systolic blood pressure, I want to use this whole range of variables, which I'm just going to borrow from over here. So I prepared this in advance, and I know which variables I want to analyze. So I'm going to delete systolic blood pressure because it's over here already. And I'll just rerun this. Now we see a whole bunch. Here again we have the summary. Now we see there are some missing values, which I'm not going to dive into right now, but you will have a course about how to, or have a lessons about how to deal with this. But we see we have some missing values, and those cases with missing values for any of the variables. So if you have for one variable that's considered here, if you have a missing value, then this case is not, or this subject is not included in our analysis, which may result in bias. So here again, the table that we're actually interested in. We can see, for instance, that if we account for all these variables, then the treatment is not a statistically significant predictor, but is borderline significant. So people who were treated, they had lower odds compared to people who did not receive the treatment. An odds ratio of 0.666 with a confidence interval ranging from 0.44 to 1.04. So basically, in this case, for a prognostic model, I'd still include treatment, right? And again, we see that, for instance, the systolic blood pressure still has pretty much the same parameter estimate and confidence interval. And we see that, for instance, a parameter like BMI is not is not a significant predictor. So we have a bunch of statistically significant predictors and predictors that are not statistically significant. So how do you go about choosing the correct ones? So we're going to go to Analyze again, Regression, Binary Logistic, and we're going to add all these variables that we just discussed. Down. Just remove this one. Okay. Add diagnosis. Add this one. Okay. And instead of using method enter, we're going to use a backward selection algorithm. We'll use the likelihood ratio test or the WALT. These are more or less interchangeable. I tend to use the likelihood ratio test. Okay, with this we click options, and here we have our rules for the algorithm. And basically, this is saying that if a p-value is higher than this 0.2 or 0.1, then remove it, and at each step, all of the removed variables are re-entered into the model and see if they have a low p-value, and if they have a low p-value, are re-entered. We're going to be a little bit less strict, and we'll opt to remove at 2 and re-enter at 0.1. Okay, and paste. Go to our syntax window and run it like this. It took slightly longer. And now we see a bunch of steps also. So now this variables in the equation table is a little bit bigger. So at the start, there's all these variables that we considered that are in the model, and going down, variables get removed until we only are left with these variables at step 8. And we see that all of these variables are meet our criterion with statistical significance, which was a p-value of 0.2. Not all of them are actually statistically significant, but we're trying not to be too greedy in this case. So we have the systolic blood pressure, weight, height, proteinuria in there, creatinine, calcium, HB, glycosylated HB, which is a measure of blood sugar, high sensitive CRP, that's just an inflammation parameter. These were all retained in the model after our selection. So, in preparation I also did a slightly different model, which I want to show you, because there are some nice example in here. Here we also have a backward selection model. And what we see here at the end is two things. I've introduced the diagnosis as a categorical variable, so there are 6 categories of diagnosis. And let me see. Diastolic blood pressure was not in here. I want to show it. Okay, I'll show it later on. So you can also use categorical variables. How you do that is you go to Analyze, Binary Logistic, and here in the option Categorical, we basically select our diagnosis and we set the reference to first and click Change. And that way you create a categorical variable like this and obtain it like that. Another thing I would like to show you is a problem called collinearity. So here we have a logistic regression model with both diastolic and systolic blood pressure in there. And diastolic blood pressure becomes a protective variable. This is highly statistically significant. But that makes very little sense, because if we look at the univariate statistics, we saw that the diastolic blood pressure in people who did not have the outcome was lower compared to people who did have the outcome. So it can hardly be a protective variable. And indeed, if we look at the univariate analysis for only diastolic blood pressure in the model, we see that diastolic blood pressure is a risk factor. So this may mean, this is called sign inversion, so a risk factor becomes a protective factor, and this may mean that you have a collinearity in your model. So basically, whether you capture blood pressure from diastolic or systolic blood pressure, you're capturing the same phenomena with a variable, and this introduces a collinearity into your model, which makes the random model kind of unstable. Yeah, this is just a bonus that you can go over by yourself, and with that I would like to round up this part of the tutorial. Now you know how to run a logistic regression model with a backwards selection algorithm to reduce the number of variables in your model. If you have any questions, you can post them in the comments below. Thank you for your attention, and next time we'll go into how to evaluate such a regression model in terms of predictive performance.